Okay, so this is our third day dedicated to functions or focused on functions. And again, functions to me are where math started to get fun and enjoyable. I wish I could teach you an entire course in functions because it sets up a new way of looking at math. And I think it makes math much, much better to appreciate and will make you a much better math student at the same time. So, functions explain everything from a home run hit by Aaron Judge or Pete Alonso to the bend of this particular graphite fly rod. It's a Scott 9.5 foot 6 weight, and the pressures of the fish fighting and everything going on there, all the vectors involved. And then it also explains, how smells linger in the air and how they travel. And in this case, over the weekend, I went hunting, but I don't hunt. I hunt with a camera. This is a friend of mine named Gerard McVicker and his dog Finn, and they have a partridge trapped inside that bunch of shrubbery there, and the dog is pointing at it, and what it's done is it's picked up the scent of the partridge and it's telling its owner, Gerard, where this partridge is, and they're waiting for the partridge to fly away. That's the big hunt. And it also explains the eyesight and how the eyes work and how they perceive the world and what's going on in there. So all of this has a mathematical relation to it. And when you stop looking at mathematics as a bunch of rules that a teacher stands in front of the room and says, just do this because I told you to, as if they're the great Oz, and instead look at it as a window into the divine mind behind the universe, now you're starting to get into some really pretty cool stuff. So, what is a mathematical function? It's a rule or a law that defines a relationship between an input variable, the independent one, the x variable, and the output or other variable, which is dependent, and we call that y, typically. A typical function would be something like y equals negative 16x squared minus 90x plus 15, and that could be involved with gravity. That would typically begin with negative 16x squared. We can envision them with function machines. I don't know why that's happening. And then another great function that you can begin to understand is exponential functions, which we talked about the other day. And they explain compound interest. If you get a chance, I teach a course called Math 1111 if you are going to want to be a teacher, and you will learn so much about how to be fiscally responsible in that course through the study of mathematics. Or also population, as you can see here, how this grows exponentially. It goes from 1 bacteria to 2 to 4 to 8. This is a picture of y equals 2 to the x. Okay? And some illnesses grow very, very quickly, and some illnesses not so quickly. So, strong immune system slows it down, a weak immune system lets it grow faster. There are 5 ways to express a function. We have a function machine, we have a graph, we have it pictured, we have it with an equation, and last but not least, function rules with tables. Okay? All right, so here is a diagram, a picture of a function. Let's have you answer these questions. Go ahead. Okay, so f of 1 becomes 1. 2 becomes 3. 3 becomes 5. And 7 becomes 13. And the way we would word that is we'd say f of 1, f of 2, f of 3 is 5, f of 7 is 13, and so on, where the inputs are 1, 2, 3, and 7, and the outputs are 1, 3, 5, and 13. Any input is a domain element, any output is a range element. Let's try these. Go ahead. So, in the beginning, numbers 1 through, or the first 4, we were really looking at seeing if you can just interpret what the picture is telling you. Now we're learning a little bit about the language of functions. What is the image of 4? We start with the 4. The image of it is 7. That's what it turns into, the output of 4. What's the image of 5? That means 5 is the input and 9 is the output. What's the pre-image of 3? That word pre-image is different than the word image. Pre-image means go backwards. So if you come out with a 3, if that's the output, what did the input have to be? It was 2. What is the output if the input is 6? So I look over input, that's on the left, there's a 6, the output is 11. List the domain elements. The domain is the set of all inputs. It's the left-hand side. Well, I don't want to say it's always the left-hand side. It's always the beginning of the function, and it's all the domain or input elements. And that's 1, 2, 3, 4, 5, 6, and 7. And the range is the set of all the outputs. And that would be 1, 3, 5, 7, 9, 11, and 13. Remember, the variable that represents domain is x. The variable that represents range is y. Okay. Now, not only do we have the standard function, which goes left to right, but we also have what we called, here's another one to do. Okay. Go ahead, start figuring these out. Okay, f of 1 would be 17, f of 2 would be 37, f of 3 is 57, f of 7 is 137. Now we'll try some more vocab questions. Okay, so the image of 4, that's what does 4 become? The output is 77. What's the image of 5? 97. What's the pre-image of 97? That's 5. So 3 was what's the image of 5? It was 97. 4 was what's the pre-image of 97? Well, that goes back to 5. Okay, pre-images go backwards. What is the output if the input is 6? That would be 117. List the domain of f of x. Domain is the set of all input values. That's 1, 2, 3, 4, 5, 6, and 7. Number 7, list the range of f of x. The range is the set of all output values. 17, 37, 57, 77, 97, 117, and 137. Okay. Now we have an inverse function. And inverse functions go backwards. They start where normally the range would be. They switch. The domain and range switch. Now remember that the domain variable is x, the range variable is y. And if you remember on the previous question where we said, write the inverse function, the very first step was to switch the x and y. And that's what happens here because the arrows are going backwards now. We switch what is the input and what is the output. The input's actually on the right, the output's actually on the left. So this is an inverse function. Okay, find those 4 values. Remember, you're going with stop and start here. F inverse of 1 is 1. Right? If we have the output of 1, normally what would be the output, but an inverse function becomes the input. It goes to 1. 5 is 2, the F inverse of 5. F inverse of 2, there is none. There's no 2 over here to have an F inverse of. And F inverse of 29 is 5. Okay, so just follow the backwards arrow. And now we have vocab questions about this, which will really help your understanding, because if you can do both f of x and f inverse of x, you have an outstanding understanding of terminology. Okay, so what's the image of 4? There is none. There's no 4 to have an image of here. What about the image of 5? Well, that would be 2. What about the pre-image of 19? Uh-oh, I hope I didn't put 4 down here. I think I did. The pre-image of 19, there is no pre-image of 19 because 19 is in the domain. So that should say none. That was my beta test that I missed. That's what I get for keeping the old question. What's the output if the input's 45? That output is 7. List the domain elements. The domain is 1, 3, 5, 6, and look at that. I was getting too mechanical here. Because it's an inverse function, we switch them. So the domain is 1, 5, 11, 19, 29, 41, 45. Don't know where this came from either, except it must not have copied over from the other one. 1, 5, 11, 19, 29, 41, 45, and list the range. The range would be, I'm going to correct these now. So, first off, this is none. List the domain of f of x. 1, 5, 11, 19, 29, 41, and 45. Make that a little bit wider. Oh, good. And this is 1, 2, 3, 4, 5, 6, 7. Okay. Watch what happens when I try to save it. You'll see where I get into these problems. Watch, it'll save this time, but it usually doesn't save. Watch, I'm going to try. So that you can see I'm not lying when I tell you where all these issues and problems come from. First, we get the wheel of death. See, look at this. The file cannot be saved right now because the file is loaded by another user at this moment. You can wait a few moments and try to save again later. It never works. So, basically, in order for me to save this now, I have to copy the whole slideshow and create a whole nother slideshow. So, I actually think I saved it under final use this. But anyway, we have this corrected. Oh, I hopefully I don't encounter more mistakes like this. But you can see when I try to save the corrections, it doesn't always save the corrections for me. So okay, this whole first section was all saved. This worked great. And then we went through the image of 4, pre-image of 5, pre-image of 19. So let's go back to this. The pre-image of 19, normally we would say that it's 4, except we're in an inverse function which goes backwards, so there was nothing before the 19. There was no pre, if you will. So there's no pre-image. What's the output if the input's 45? That would be 7. Now list the domain elements. Remember, we switched the x and y because it's an inverse. So the domain is this list of numbers on the right. 1, 5, 11, 19, 29, 41, 45. And the range is a 1, 2, 3, 4, 5, 6, 7. Okay. Hopefully it saves at some point in the future. F of x equals 3x minus 4. Evaluate each of the following in the function f of x. Go ahead. Okay. F of 3 is 3 times 3 minus 4. So f takes the input. This is important to be able to read it this way. F takes this function f, this function box f, takes the input, which is x. That's what x means. Don't say x, say input. F takes the input, multiplies that very same input by 3, and subtracts 4. So if the input is 3, 3 times 3 is 9, minus 4 is 5. I don't know, that was just a brain spasm. Next, 3 times the input, which is 5, is 15 minus 4 is 11. Next, the input is 10, so 3 times that input of 10, which is 30, minus 4 is 26. Don't know where those mistakes are coming from. 3 times negative 4 minus 4 is negative 17. That's, no, it's negative 16. Why am I, this mustn't have saved from before either. So I'm going 5. That's 11, that's right. This is 26. This is negative 16. Let me just look at the next two real quick. Yep, that also had it. All this means it was a previous version that didn't save like you saw before. 36 minus 4 is 32. Okay, play from current. That would take a long time. So, again, back to the beginning. F takes the input, multiplies it by 3, subtracts 4. So 3 times 3 is 9, minus 4 is 5. 3 times 5 is 15, minus 4 is 11. 3 times 10 is 30, minus 4 is 26. 3 times negative 4 is negative 12, minus 4 is negative 16. 3 times that input of negative 7 is negative 21, minus 4 is negative 25. And 3 times 12 is 36, minus 4 is 32. Okay, let's see you try the other side, and hopefully I didn't have any issues with saving from an old version. Go ahead. Okay, so it's very important here to see that G takes the input, squares the input first. That's very important with the order of operations here. We square the input first, multiply by 2, and add x. So 2 times 3 squared plus x itself, whatever the input was. 2 takes the input, G takes the input, squares it, multiplies by 2, and then adds that original input. So notice the x for input in both cases was a 3. 3 squared is 9, times 2 is 18, plus 3 is 21. Substituting it 5 for input. 5 squared is 25, times 2 is 50, plus the 5 that was the input, 55. Now you can literally just type this on your calculator, every place that you see an x. In fact, you can do it even easier than that. You can go into your table function under y1, type in 2x squared plus x, hit table, and then go to where the input is 10. It'll tell you the output's 210. Go to where the input's negative 4. It'll tell you that the output is 28. Go to where the input is negative 7. That first column is the input. And that would tell you that you're going to get 91. Or, if you wanted to, you could do 2, exactly as I type here, parenthesis 12 squared minus 12, or I'm sorry, plus 12, because it's positive there. And that would work out to be 300. So, the calculator will do these for you if you don't want to get driven too crazy. You can use table, which I think is the best way, particularly if we're going to hit it again and again and again. Or you can just input the data into the regular math keys. Now, the reason I think it's so important to be able to say to yourself, F takes the input, multiplies the input by 3 and subtracts 4, or G takes the input, squares it, multiplies it by 2, and adds back the input, the original input. I think that's so important for a lot of things so that you can really understand what a function is doing, but we now get into an idea that we call the composition of functions. And that is when you do not just one function, but 2. And in this particular case, this is a picture of what we call G of f of x. So you start with f of x, and then you change that result, that the output from f becomes the input to G, which changes it a second time. And that output is called one of two things. It's either called G of f of x or G of f. They didn't put the of x, but that's not a 0 there or an O in the middle. That's a composition symbol. So let's begin to explain this to you. Let's start with the function G of x is equal to x plus 2, and we're going to input 3, 4, and 5. What would the output look like? Go ahead, you tell me. Remember, G takes the input and then adds 2 to the input. So 3 plus 2 is 5, 4 plus 2 is 6, and 5 plus 2 is 7. Very simple function to do. Domain 3, 4, 5, range 5, 6, 7. G simply takes the input and adds 2. Now, the f function squares the input. So if I add, oh, there's all my arrows. If I then add a place for f to work on its input, notice that the range of G, the outputs from G, become the inputs or the domain for f of x. So for f of x, I have to square each of them. So what's 5 squared? 25. What's 6 squared? 36. What's 7 squared? 49. Not sure why that happened, but anyway. When we look at the composition of functions, what we're saying is that f of G of 3 goes all the way to 25. F of G of 4 goes all the way to 36. F of G of 5 goes all the way to 49. Okay? All right. I would write it in one of two ways. One way to write it is f of G of 3 is 25. The other way is fog, but this is not an O in the middle there. That's a composition symbol. So that also means f of G of 3. They're both accepted notations that both stand for f of G of 3. The next one, f of G of 5 is 49. I don't know why that one went there. F of G of 4 is 36. and then the second way to write f of g of 5 is 49. It's strange why I went there. Here's the second way to write f of g of 4 is 36. And the other way was fog, and I don't know why they didn't do that. Okay, so let's start a second slide. G of x is equal to x minus 2. F of x is equal to x squared. So now it's not plus 2, it's minus 2. Go ahead. What would we get for the output or the range of G? Okay, G of 3 is 1, G of 4 is 2, and G of 5 is 3. So 3 becomes 1, or the image of 3 is 1, the image of 4 is 2, the image of 5 is 3. But we want to know what f of g of x is, so I create another area for range, and the domain for f of x is now 1, 2, 3. What would the range or set of outputs be? Well, 1 squared is 1, 2 squared is 4, 3 squared is 9. I don't know why this is doing it a second time, but whatever. I'm going to draw the arrows. Here's the big thing. F of g of 3 is 1. And I could also write that using the composition notation. F of g of 4, well, let's do 5. F of g of 5 is 9. F of g of 4 is 4. I wrote it the same here. I will look for the composition function. Or f of g of 4 is 4. Okay? So this pictorially is what's going on. There's an initial change by g, and then f runs with it. He takes what it was changed into and then turns it into its output value. So that's why we like to say f of g of 3. When you read these parentheses, you start from the inside out, okay? Just like simplifying algebraic expressions. First you find g of 3, then you find f of it. Or you read it backwards if it's in the second notation. First you find g of 3, then you find f of it. Okay, so this first one says find f of g of 3. So first you have to find g of 3, and then you have to hand that to f. Go ahead. Okay, so f of g of 3 is f of whatever g gives you, which is 2 times 3 squared. 3 squared is 9, times 2 is 18. So now I have to do f of 18. And f takes whatever the input is and multiplies it by 3. That's why it's so important to be able to read this way. 3 times the new input, which is 18. 3 times 18 is 54. Okay. Now, we just did f of g of 3. Now we're going to do g of f of 3. So you remember the commutative property? Some things in math are commutative. For example, addition. 2 plus 5 is 7. 5 plus 2 is 7. But subtraction is not commutative. 2 minus 5 is negative 3. 5 minus 2 is positive 3. Let's see if composition is commutative. We did f of g of 3. Now let's do g of f of 3. So start with the input going into the f function and finish with it going into g, the exact opposite order of the previous problem. Go ahead. Okay, so if I give an input of 3 to f, 3 times the input is 3 times 3, which is 9. Now I give 9 to g, and 9 specifically takes the input, squares it, and multiplies by 2. So 9 squared is 81. 81 times 2 is equal to 162. Now let's have you try both numbers 3 and 4 and see, are they equal or are they not equal? We can already see that it's not commutative, but let's just check and see for this case. Go ahead. Okay, so g of f of negative 4 means that we're going to give a negative 4 to f. It takes the input, multiplies by 3. That gives me negative 12. So now I'm going to input a negative 12 into g, which squares the input. That makes 144. times 2 is 288. Now f of g of -4 is the opposite order. I hand the -4 to g, it's going to square it and make 16, multiply by 2 and get 32. Then I hand the 32 to f, which is 3 times whatever you give to f. The input is 3 times 32 is 96. Okay. Now a little bit of a strange kind of composition here. What's g of 9? Okay, so I hand a 9 to G, and G takes whatever it's given, it squares it, and then it doubles it, and oh man, I made a mistake here. This should be 9 squared and not 3 squared. 2 times 9 squared, which 9 squared is 81. 81 times 2 is 162. So this is now becomes 2 times 162 squared. And boy, oh boy, that's going to be a big number. Oh man, my calculator's over there, so let me just do it on my phone. 162 times 162 is 26,244, and then I do times 2, and I get 52,488. Okay, let's go back to plate from, and now we've done the first 4, and now back to the 5th one. So g of 9. So I forgot to change the 3 into a 9, but I have it right here. G of 2 times 9 squared. 9 squared is 81. 2 times 81 is 162. And then it goes to g again, which takes the 162 and squares that because it's the input, multiplies by 2, and that works out to 52,488. Okay, let's see you try g of f of 5, our last composition question. Okay, so first I give a 5 to f. F takes whatever it's given and it triples it. So the input times 3 is 15. And now for g of x, it's going to be 2 times 15 squared because g takes the input, squares it first, then multiplies by 2. 15 squared is 225 times 2 is 450. So there are some good composition questions for you to work on. Okay, next, relations and functions. Functions are special kinds of relations. Relations are more broad. It's like saying a whale or a mouse or a dog is a special kind of mammal. So functions are special kinds of relations. In a function, every input must have its own unique output. So there's 2 things there. Every single input has to have an output, okay? If it's in the domain, it has to have an output. And it also has to have a unique output. So in other words, you cannot get 2 different outputs from the same input. So this is a function on the left. 1 becomes 4, or the image of 1 is 4, the image of 2 is 4, the image of 3 is 12, 4 is 16, 5 is 20. That's fine. It's legit. It's a function. Each domain element, 1, 2, 3, 4, 5, has one and only one, a single, unique, distinct image. The second one is not a function because if you notice, 4 does not have its own unique output. For 4, you have outputs or its own distinct output because 4 becomes both 4 and 5. So that's the problem. That's not a function. Now, these were pictures of functions. The next one is tables, another way to represent a function. So the first one is a function. Notice for the input values for the domain, I have 1, 2, 3, and 4. Not a problem. They each have their own output. 1 goes to 8, 2 goes to 17, 3 goes to -3, and 4 goes to 17. Now, I could have had 1 going to 8, 2 going to 8, 3 going to 8, 4 going to 8. That's all fine. I just can't have any domain element repeating. So here's one that's not a function. 1 becomes 8, 2 becomes 17. So far, so good. 3 becomes -3. So far, so good. 3 becomes 17. Now we have a problem. Not because of the 17. That's fine. That's not an issue. But 3, the image of 3 cannot be both negative 3 and positive 17. What we're saying with functions is this. When your function comes out, you're going to get a single answer. You can't input a value and get 2 different answers in a function. Then it's not a function. It's just what we call a relation. So take a look at these two and decide if they are functions or not a function. Okay, so for x becomes 1, 1 becomes 5, that looks good, 2 becomes 10, 3, 15, 4, 20, yeah, that's fine, right? There's no single domain element that has 2 different images. But now look at the last one. So the first one is a function. And the last one, 1 becomes 8, so far so good, 2 becomes 17, and 2 becomes negative 3, that can't be, impossible. So that's not a function, okay? All right, the happy recap on our 3rd day of functions and functions overall. Describe composition of functions. So composition is a series of functions where you begin with a domain element, which becomes a range element for the first function, which then becomes the input of the second function. Okay? Next up, what's the difference between a relation and a function? Pretty simple. In a function, every single domain element has to have one and only one output. You cannot have 2 different outputs. The output has to be unique. Okay, number 3, how do you find the inverse of a function? Switch the x and y, solve for y. All right, that's the end of video 2 for lesson 17.